It's true. Alright, so yesterday we looked at radical functions, now we're moving on to rational functions. Which is pretty much just a polynomial divided by a polynomial. Okay, so the rational function f of x is given by a polynomial in the numerator divided by a polynomial in the denominator. So it's a fraction of polynomials. Okay, one thing to note is we can never divide by 0, which means that the denominator polynomial cannot equal 0. Okay, so we'll have a restriction if we have a variable in that polynomial. So a few examples of rational functions could be x plus 2 divided by x minus 1, 1 over x squared minus 9, and x squared minus 4 all over x plus 2. So going back to the notion that d of x cannot equal 0, basically we can't divide by 0, there's a few discontinuities that could happen. So let's take a look at these examples. Just looking at this denominator, what could x not equal? What would be a non-permissible value? Good. Write that in. X can equal 1. Okay, from the next one, x squared minus 9 can't equal 0. So what values of x?
Square root of 9. 3.
Okay, x cannot equal 3, but it also can't equal negative 3. So x can equal positive or negative 3.
Well, that's actually right, but what'd you say? It's root of 9.
Okay, and for the denominator x plus 2, we have x cannot equal negative 2. These are non-permissible values or restrictions on the denominator. Okay, let's take a look at this example though. 1 over x squared plus 1. X is being squared, so no matter what value you plug in for x there, you will get a positive outcome. And if you have a positive number plus a positive number, will you ever get to 0? No. So in this case, we actually have no restrictions at all. X can be anything. Okay, there's no discontinuities on a graph like that. Okay, so if we were to describe the domain, x could be any real number. So with discontinuities, Bruce, your personal hygiene is getting in the way of class. With discontinuities, there's two of them. There's an infinite discontinuity, and that's leading us to a vertical asymptote. Or we have points of discontinuity, which is just like a hole in the graph or a point that's missing from the graph. We're going to look at pretty much vertical and horizontal asymptotes in this lesson, and the next lesson will be on points of discontinuity. So let's just explore a general graph of a rational function, and the one that we're given is 1 over x minus 1. If we were looking just at the denominator, what would be your non-permissible value? 1. So we'd say that x cannot equal 1. That's your NPV, non-permissible value. Using this function, a rational function, 1 over x minus 1, let's just plug in some values of x into the equation to get some values of y. From there we'll plot the points and see if we can determine the shape of the graph. Okay, so if I plug negative 5 in there, I get 1 over negative 5 minus 1, so 1 over negative 6. What's that as a decimal? Someone help me out. Please.
0.16.
Repeat it?
Yep.
Okay, so we have negative 0.16 repeated. If we were to sum in x equals negative 2, we get 1 over negative 3. So that's 0.3 repeated. If we were to plug in negative 1 for x, we'd get 1 over negative 2. And that's negative 0.5. If we plug in 0, we get 1 over negative 1. So just negative 1. And what happens when we plug 1 into the x? We get 0, which we can't divide by. So the function will be undefined here. It does not exist. Okay, plugging 2 in for x, we get 1 over 2 minus 1, so 1 over 1, 1. Plugging in 3, we get 1 over 2, so 0.5. Plugging in 4, we get 1 over 4 minus 1, or 1 over 3. So 0.3 repeated. And if we plug in 5, we get 1 over 5 minus 1. So 1 over 4 gives me 0.25. So let's just plot some of these points. And I'm actually going to start right with x equals 1. No matter where we are on the graph, when x equals 1, it will not exist. So using a dashed line, this is what we call our vertical asymptote. And that exists when x equals 1. So the equation of that asymptote is x equals 1. The restriction on the domain is that x cannot equal 1. But when we're describing the vertical asymptote, x equals 1. Now that we've got that marked out, let's plot a few points here. So we have when x is negative 5, we're at negative 0.16. Okay, very small. When x is at negative 2, we're at negative 0.3. Where's my x-axis here? 0.3 repeated, so about there. Okay, when x is negative 1, we're at 0.5, negative 0.5, sorry. And when x is 0, we're at negative 1. I'm going to have to redraw this asymptote. Someone was messing with the card. Okay, now on the positive side, okay, when x is 1, the graph did not exist. When x is 2, we're at 1. When x is at 3, we're at a half. When x is at 4, we're at 0.3 repeated. And when x is at 5, we're at 0.25. So we have a few points, but if that was me looking at a rational function the first time, I wouldn't really know how it connects. So I'm going to allow a little cheat. Okay, we're going to go to our calculator just to explore rational functions as an introduction. And then hopefully you guys will see the trends as you do more and more. Okay, so plugging into your y equals, we're going to go 1 divided by x minus 1. And then let's graph it. So there is my rational function. Let me just move this so you guys can see it better. That should do. Okay, so on the left side of the vertical asymptote, we have a curve. It's concave down. Okay, and on the right side of the vertical asymptote, kind of have like this concave up curve. Okay, so if we follow the points that we've already plotted, looks like it's going like that. And like that. So let's just talk about the graph, what we see so far. As the graph's x values are getting smaller, what do you guys notice about the y coordinates? They're getting bigger. So as the x coordinates are getting smaller, so from 5 to 4 to 3 to 2, okay, we're going from 0.25 to 0.3 repeated to 0.5 to 1. The y coordinates are getting bigger. Okay, and eventually what's going to happen is it's just going to be going to infinity. Do you think it will ever cross this line x equals 1? Will it touch that? No, because it's a discontinuity, it's our non-permissible value. Okay, so as x gets smaller, we're approaching infinity. As x gets bigger, any guesses where this graph is approaching? The x-axis, good. And I deleted it off my calculator, but I'm going to show you guys a little trick. So we put that in there again. So what you can do is you can actually use your table of values, so second graph, and we can see as x is getting bigger, so I'm just going to keep scrolling down, letting x get bigger, where does it look like the y values are approaching? Okay, it's getting smaller and smaller and smaller and smaller, and they're getting very close to 0. If I went to x is infinity, we still wouldn't touch 0. It would be approaching 0, but it wouldn't touch 0. Okay, so you're absolutely right, Booker. That is the x-axis that it's approaching. Okay, and what we're going to call this x-axis is a horizontal asymptote. And what's the equation for the x-axis? Y equals 0. Good. Let's look on the left-hand side what's happening. As x is getting smaller and smaller, we're getting more and more negative. Where is the graph approaching? That horizontal asymptote y equals 0. And as x is getting bigger and approaching x equals 1, our vertical asymptote, the graph is getting smaller and smaller and smaller. Where do you think it's approaching? In the y coordinates, where is it approaching? Negative infinity. Good. So we could do the table of values to confirm that. Basically what you get, I'll just throw it in there quickly. Okay, if you plugged in these x coordinates into the equation 1 over x minus 1, you would get these values. And it's just showing that as x is getting closer and closer to 1, it's getting smaller. Okay, it's going to be approaching that negative infinity as we get closer to 1. And on the other side, so from the right side of the graph, as we're approaching 1, do you see how the values, sorry, 1.01. The y values are getting smaller and smaller and smaller. So as x is getting bigger, notice that it's going down. Oh, sorry.
Aren't you?
Pardon?
Are the numbers not stuck on the
I maybe
chart?
I maybe
think
wrote
it
it
goes
down wrong.
negative.
I was going off of memory. Yeah, it should be 110. That's why it's not making sense. Let's just make sure here. I apologize. Yep, and negative 10. Negative 100, negative 10. See, that's why you don't go off memory. You have to actually plug them in. Thanks, Joe. Now we got it right. Okay, let's just look. As x is getting bigger, as x is getting bigger, the values are getting considerably smaller. And eventually, as we get bigger and bigger and bigger on our x values, we're going to be approaching the x-axis at 0. Okay, we've already talked about it, but I just wanted to show you with these values. Okay, and I'll just summarize this side again. As x is getting bigger and bigger and bigger, as we're approaching this asymptote from the left-hand side, what do you guys notice the values are doing? They're getting smaller and smaller and smaller, and they're going to approach negative infinity. So let's just summarize a few things. Describe what happens when the value of the function, describe what happens to the value of the function as x gets more and more positive. Okay, what's happening as x is getting more and more positive? Okay, and sorry, did that one say from left to right? Anyways, I was thinking about f. Okay, it's approaching the x-axis. Okay, and same thing as x is getting smaller and smaller, it's approaching the x-axis. Okay, so that's getting closer to our horizontal asymptote. Question F. Describe what happens to the value of the function as x gets more negative. Okay, again, it's approaching that horizontal asymptote. As it gets negative, it's getting closer and closer to the x-axis, y equals 0. So basically, E and F are the same thing. Okay, no matter which way you're going, as x gets more negative, you're approaching that x-axis. As x gets more positive, you're approaching the x-axis. Part G, you just have to circle here. So as x gets closer and closer to the non-permissible value of 1 from the left, the value of the function is approaching where? So as we're getting closer and closer to the line x equals 1, what is happening to the y coordinates? Where are we approaching? Negative infinity. So for the last one there, just circle negative infinity. And then the bullet, or the final bullet says, as x gets closer and closer to the non-permissible value of 1, this time from the right, the value of the function is approaching positive infinity. Okay, so just circle positive infinity. So we've already talked a lot about vertical and horizontal asymptotes from that first example, but they're basically a line where the graph does not exist. Okay, the vertical asymptote we figured out comes from the denominator, the restriction on that denominator, our non-permissible value. Okay, and the horizontal asymptote, that's going to come from, there's 3 rules on how to determine it, and we'll go through a few investigations to find those. Okay? So let's check out 3 over x. First of all, just looking at the denominator x, what would be your restriction on the domain? What's your non-permissible value? 0. So for our domain, x cannot equal 0, and everything else will be real numbers. So if x can equal 0, we've already found our vertical asymptote, and the equation will be x equals 0. And let's draw that on our graph right away. Okay, now what we're going to do is we're just going to graph this function and see if we can find our horizontal asymptote. So 3 divided by x. Now by looking at it, it's looking like it's approaching the x-axis again. But if you want to be sure, just check out your table of values and you can verify. Okay. As x is getting bigger and bigger and bigger, where does it look like it's approaching? 0. Okay, so we verified using our calculator. Which means I have a horizontal asymptote at that x-axis. And HA means horizontal asymptote. The equation would be y equals 0. So for part F, the horizontal asymptote is y equals 0. And roughly we can draw in our function without using actual points. That's the general shape of it. Okay, so we're approaching the x-axis as x gets bigger and bigger. We're approaching infinity as x gets smaller. We're approaching as x gets bigger from the left, we're going to be approaching negative infinity. And as x gets smaller, moving to the left, we're approaching that x-axis. Okay, we're never going to touch or cross these vertical or horizontal axes. It's never going to touch. It's going to approach it, get really close, but not touch. So knowing that we have a horizontal asymptote and we can see what the function looks like, let's state our range. Okay, and it's basically y cannot equal 0. Now there's going to be 3 rules for finding horizontal asymptotes, so I'm just going to point them out now so it's relevant rather than talking about it later. So let's take a look at 3 over x. Okay, and we're just going to compare the degree. Would you say that the degree of the numerator is bigger or smaller than the denominator? First of all, what is the degree of 3? It's smaller, but what's the degree? It's actually not 1. The exponent on the denominator is 1, so the degree is 1. This one has an invisible variable with an exponent 0. Because anything to the power of 0 is 1, so it leaves that constant all by itself. So the degree of the numerator is 0. The degree of the denominator is 1. So we would say that the degree of the numerator is less than the degree of the denominator. And if that's the case, we'll always have a horizontal asymptote of y equals 0. Okay, so if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote will always be y equals 0. Now, if you forget that, where can you go on your calculator to check the table of values? Okay, so you can always see what's happening as x moves right or left, as it's getting bigger or smaller. Where is it approaching? Okay, so that's the first rule for horizontal asymptotes. Let's take a look at another rational function and see if we can come up with the second rule. So based on, let me just erase this first. Based on the denominator in this one, what would be the restriction? What's your non-permissible value? From x plus 1, what can x not equal? -1. So then the domain would be x cannot equal -1. And the rest of the graph includes real numbers. So if that's our restriction on the domain, our vertical asymptote in part C will be the equation x equals -1. And let's put that on our graph. Okay, our vertical asymptote is at x equals -1. So now let's graph it and get the general shape of the graph. So 2x divided by, in brackets, x plus 1. Okay, there we have it. Now I haven't given you the clue on how to find the horizontal asymptote. So if you guys were just to look at the graph, where would you think this line is approaching, and where would you think this line is approaching? Where is it getting closer and closer to? 2. It's a good guess, but if you're unsure, go to your table, and as x is getting bigger and bigger, it looks to me like it's approaching 2. So it's increasing by such small amounts, but it's not going over 2. It's approaching 2. Okay, so I think it's pretty fair to say that the graph is approaching 2. It's not going to actually touch 2 though. So let's draw a horizontal asymptote at x equals 2. Sorry, y equals 2. So now that we've put our few restrictions, so the horizontal and vertical asymptote, we can draw the shape of the graph. So we've estimated that the horizontal asymptote was at y equals 2. We've shown it with the dashed line. Now let's state the range. Y cannot equal 2, and the rest is a set of real numbers. So from the example 2x over x plus 1, let's just compare the degree again. Would you say that the degree of the numerator is bigger, smaller, or equal to the degree of the denominator? What's the degree of the numerator? 1. Good. What's the degree of the denominator? 1. So we have the same degree. The degree of the numerator is equal to the degree of the denominator. And when that's the case, our horizontal asymptote has a unique case. It's going to be y equals a over b, where a and b, are the leading coefficients. So taking a look at 2x over x plus 1, my leading coefficient is 2, For the numerator, my leading coefficient is this imaginary 1. So if I were to divide 2 divided by 1, you get your horizontal asymptote, which we found to be 2. So same degree in the numerator and denominator, you just take the leading coefficients and divide them. Third scenario, we have x squared divided by x minus 2. What's the restriction on the denominator? You guys must know this well, because you're getting bored of it. Okay, we have x cannot equal 2. So they don't care about the domain on this one until the very end. So let's just draw the vertical asymptote to start. Okay, vertical asymptote is that x equals 2. If the graph will never touch that, let's just jump to part D. What's your domain?
X can equal
Yeah, x can equal 2, and we have a set of real numbers outside of that. Okay, now let's graph this. So x squared divided by x minus 2 in brackets. Okay, so the last few examples we've seen like a very distinct horizontal asymptote, or sorry, vertical asymptote, and a very distinct horizontal asymptote. But here it's like a whole section where the graph isn't going to touch. Vertical and horizontal asymptotes are lines that the graph is going to approach but never touch. So here, do you think that we have a horizontal asymptote? No, it's actually like a big gap, so it's not a specific value. So in this case, there is no horizontal asymptote. So for part C, does the function have a horizontal asymptote? No. Okay, that's the general shape of the graph. They're still asking us to find the range of this function. So we're going to have to use some features on our calculator to figure out the minimum and the maximum point. And by the y values, we'll get our range. I wish I didn't quit this calculator. I'm going to put it back in again. So x squared divided by x minus 2. Okay, let's start by calculating the maximum. You're going to go second trace, number 4. And my cursor is here, so I'll go left bound to that point, enter. Right bound to that point, enter, and then guess, enter. So some of the values might be different on your calculator, but I have 1.4523 times 10 to the power of negative 6. Okay, that value is so small, it's really close to 0. I think just based on the zoom of my calculator, it's not showing 0. Same thing with here, it's so close to 0. So we can say that our maximum is at 0, 0. Okay? Now we're going to calculate our minimum. So second trace, number 3, and just watch as I move my cursor. I'm going to move it to the right, and it's on the lower curve, and all of a sudden it's just going to jump up to the top curve. That's where I want to be. So enter on left bound, enter on right bound, and guess. And 3.9 repeated and 8. So if I were to round, I'd get my minimum at 4, 8. So just looking at the y coordinates, because that's how I'm going to find my range. Okay, y exists bigger than 8 or equal to. So y will be greater than or equal to 8. and for the maximum, it's going to be smaller than or equal to 0. And the rest of the graph is real numbers. So the third summary, I guess we can say, is for this graph, we had x squared over x minus 2. Looking at the degree, we have degree 2 in the numerator, we have degree 1 in the denominator. So whenever the degree of the numerator is bigger than the degree of the denominator, we can say that we have no horizontal asymptotes. Okay, so these are the rules for figuring out your horizontal asymptotes algebraically without using the trace feature on your calculator. Skip over that. Let's go to page 460, please. So pretty much the rules that we just talked about here are all summarized lovely and nicely for you on page 460. Okay, vertical asymptotes, where do we get those from? The vertical lines, where do we get those from? The denominator, it's the MPV on the denominator. Okay, and the horizontal asymptotes, we came up with 3 rules. So just to summarize those, if the degree of the numerator is less than the degree of the denominator, then we have a horizontal asymptote at y equals 0. Okay, for example, when we looked at 3 over x, our horizontal asymptote was y equals 0. Degree of numerator was smaller. Okay, the second rule, if the degree of the numerator is equal to the degree of the denominator, just like this example, 2x over x plus 1, then what we do is we take the ratio of the coefficients, so 2 divided by 1, and that will give us our horizontal asymptote. In this case, it was y equals 2 over 1, or 2. And the last scenario is when the degree of the numerator was greater than the degree of the denominator. For example, x squared over x minus 2, we had no horizontal asymptote. So let's see if those rules have sunk in. Algebraically, we have to determine the equations of the asymptotes of the graph without using a calculator at first, so algebraically. I'm going to start with the horizontal asymptote. Okay, let's look at the degrees. We have x squared, x squared. So both degree 2. What is my horizontal asymptote? Degree of the numerator is equal to the degree of the denominator. So heard it over here? We said it? 1 over 2. Good. We take the leading coefficients, 1 divided by 2. For the vertical asymptote, we need to factor the denominator.
Junior class change.
Okay, so we start with 2x squared minus x minus 3. We need to figure out 2 numbers that multiply to negative 6 and add to negative 1. Those numbers are negative 3 and positive 2. So because we have a leading coefficient that's not 1, we have to factor by decomposition. So 2x squared plus 2x minus 3x minus 3. Factoring with 4 terms, we must factor by grouping. First group, we can take out a 2x. We're left with x plus 1. And the second group, we can take out a negative 3, and we are left with x plus 1. Both groups have x plus 1 as a common factor, so we can factor that out. X plus 1 goes in front, and we're left with 2x minus 3. So if our function is x squared plus x minus 6 all over our factor denominator, x plus 1 times 2x minus 3, we get our vertical asymptotes from the restrictions on the denominator. Okay, what can x not equal? -1 and 3 over 2. So are those my vertical asymptotes? Kind of, but not really. They're the restrictions on the denominator, but whenever we state our vertical asymptote, it's actually the equation. So x equals -1 and 3 over 2. Okay, so just be careful. These are the NPVs, and this is for the vertical asymptote. NPV is non-permissible value.